Good morning. So we continue from where we stopped last week. This lecture note is lecture note 3. So these are some of the items we are going to be looking at today, or these are the key topics we shall look at. We shall be looking at today. We may not be able to round up today because this topic may require us 2 sessions. So these are the reference materials. So we start with heat treatment. What is heat treatment? And then we look at heat treatment of steel. One of the primary advantages of steel is the ability to attain high strength through heat treatment while still retaining some degree of ductility. So from this first sentence, you know that heat treatment is basically used to improve the property of what? Of alloys. But in this case, since we are looking at a steel, then it means of what? Of steel. This ability of steels to be strengthened is a direct consequence of the amount of carbon content. So there are two things here. For steel, we should know from the background that for steel, the carbon content is important in the strength of steel. So the higher the carbon content, the higher the strength. Can we see from this diagram first by the left? The strength, you can see as the carbon content increases, the strength what? The yield and ultimate strength what? Increase. Are we together, please, class? You can see it's increasing. Can you see my mouse head? So this is telling us that the strength of steel depends on what? Carbon content. Or I will say the strength of steel or cast iron, because steel is the carbon content is from what? From 0 to 2%, while cast iron is from 2 to what? 4%. Right? But then as the strength increases with respect to the carbon content, the ductility what? Decreases. So it's a trade-off. So you have to look at that's why here we said we can still have steel with heat treatment at a very high improvement while maintaining some degree of what? Ductility. We can see that as the strength increases, also hardness is similar. As carbon content increases, the hardness also what? Increases. Though what here, this diagram means here is this is the heat treatment, this is the carbon content. So here we have talked about the carbon content, and then we look at heat treatment. Heat treatment basically is used to improve the mechanical property of steel, either the strength or what, or to increase some amount of ductility. Ductility is also mechanical property. So we have different types of heat treatment. We have spherodising, normalizing, and then what? We have conventional heat treatment. So the second one here, we have two types. Annealing is these two processes, while conventional heat treatment is what? Is this. So you can see conventional heat treatment significantly increase the property of steel. Can we see it from here? I hope you can see the curve.
Yes, sir.
So what is heat treatment? Carried out on metallic alloys to improve what? Mechanical property. Basically, these mechanical properties are what? Strength and hardness. And this is in the case of what? Conventional heat treatment. So this one here, you can see where my mouse head is the conventional heat treatment, which significantly you can see, right? It inflates the hardness. While the first one here, annealing process, is these two. So we are going to start with annealing. So here we are saying that as the carbon content increases, strength and hardness what? This is for per carbon content because steel is dependent on the carbon content. And then we shall start with annealing. So let's look at these processes. What is annealing? These are the two major heat treatments, right? Annealing and conventional heat treatment. So let's start with annealing. Annealing involves normalizing, spherodising, and others. So annealing is heat treatment in which a material is exposed to an elevated temperature for an extended period of time and then slowly cools down. So you raise the temperature, you heat it up, and then hold it for some time, and then you slowly cool. This is what we call annealing. Typically, it is carried out to relieve what? Stresses, to increase softness, ductility. So as I said earlier, ductility is also a mechanical property, produce specific microstructure. So if you look at the first diagram here, annealing, it doesn't significantly, it just very lightly, slightly improve the mechanical property. Can you see? The mechanical property is strength, hardness, and others, right? So you can see the hardness increasing, though this is with respect to carbon content, right? but also with respect to what the heat treatment process. This is the one with only carbon content, hardness and strength. Also, it as strength increases, also hardness increases, though there is no directly here for hardness. So any annealing process consists of 3 stages: heating. This is the heating. Can you see? This is temperature curve. You heat it. This is the time, the horizontal, and so you hold it. This you can see a long period of time is for the holding, right? We have shorter period of time for heating. Then holding means maintaining that temperature without increasing it, and then you slowly cool. So in this case, this is the microstructure initially, right? A brittle nature, brittle, something like a stick, and this is the final microstructure. You can see it. These lines have turned to circle, and it's difficult to break circles, isn't it? And so this is more ductile. I hope we are together, please.
Yes, sir.
Yeah. So basically, it improves what? Ductility. So this is the final microstructure. So basically, it's heating, holding, which is soaking at that temperature, and then cooling. And what it does is to improve what? Most important is to improve ductility, because initially we can see the material is what? Is more brittle nature, but after the heat treatment, it's more of what? It has become a bit ductile. This cementite, you can see, they have turned into circles, right? We are going to see, already we know what cementites are, isn't it? In 309. So let's continue. So we don't want a great change in temperature, else it will induce internal stresses. So it has to be a bit, it has to be from experience, right? The heating process, so that it should not be heated in such a way that it is too steep. Because if it is too steep, then there is no time for it to allow for change in microstructure, right? So if the rate of temperature change is too great, temperature gradients and internal stresses may be induced, and this can cause internal cracking. As you said earlier, it is done to relieve stresses. We've seen ductility, whereby with the process, ductility can before and after, right? Microstructure changes. And so let's see what causes internal stresses. Internal stresses can be developed due to plastic deformation. When there is plastic deformation, the stress level of the material has significantly increased. At that surfaces of the cutting, the stresses we are close to the grinding surface are very high, right? And so this can cause internal stress. When you have non-uniform cooling of a piece that was processed or fabricated at an elevated temperature. Even this here, when the heating or the cooling is done very fast, rapid, too rapid, there is not enough time for it to microstructural adjustment. And also in this case, so that's why we said non-uniform cooling. So when this cooling is carried out very fast, and then when there's a phase transformation that is induced upon cooling, in which parent and product phases have different densities. So we are going to see later. Okay, we have done this in 309, where you have alpha and beta, right? You have two materials. Are we together? Class.
Yes, sir.
In 309, we have when you have two phases, here is alpha and beta. So when there is heating, here this alpha and beta turns to what? Alpha plus liquid. So during cooling, if the cooling is not done well, then there is not enough time for alpha and beta to be fully formed, right? So this is what can cause also internal stresses, because alpha and beta, they are product of different metals, right? Here is beta and here is alpha, and different metals have assuming it's lead and tin, they have different densities, right? So the non-uniform cooling during or after heating to form alpha and liquid, if the cooling is not done uniformly, then you may not fully have the beta, or you are cooling from alpha and beta to either beta stage, right? And when you are cooling from beta here, you expect that after cooling, you will have alpha and beta. So if the cooling is not properly uniformly done, it could result in what? Internal stresses as a result of different densities of the product phases. The product phase is the alpha and beta. So these residual stresses are not removed. They are still there. So this may be eliminated by what? Annealing, stress annealing. Right? So let's look at the different procedures of annealing. So all these issues here, internal stresses as a result of this process, can be removed by what? Annealing. So annealing does two things: improve ductility and what? Remove internal what? Stresses. So let's look at the different types of annealing here. The first one here is normalizing. It is used to refine the grain size. Here in this case, we are looking at a coarse grain size to finer grain size. So that we can have fine grain paletic steel that are tougher than the coarse grains ones. Here it's done in what involves heating at least 55 degrees above the upper critical temperature, holding to austenize, and then cooling in air. So this is done cooling in air, while full annealing, heating above 55 degrees above the upper critical temperature, A3 and A1. This is called the L shape, while normalizing here is like the V shape we are going to see. Holding to form austenite and cementite. But in this case, the cooling is done in a furnace. So the difference between this and this normalizing and full annealing is that full annealing, the cooling is done in the furnace. And this is usually carried out on what? On steels that have experienced, in this case, low and medium, that have experienced extensive plastic deformation. So, as I said earlier, when there's plastic deformation, internal stresses are what? Are generated. And the first one is carried out on what type of rolled steel? On alloy steel that's plastically deformed, for example, by rolling operation. So this one is medium and carbon, while this one is alloy steels. So you can see normalizing. Can you see the V shape here? Can you see my V? The lighter ash. Are we together, please, class? Hello,
Yes,
class.
sir.
You can see the lighter ash, right? V, like a V letter.
Yes, sir.
So the V letter here is the A3. You can see the A3 is one part of the V, A3, and the ACM is the other part of the V going up. The A3 is the one going down here, and the ACM completes the V. So it means this is your phase diagram. I'm just bringing this for you to understand. Already we did this in 309. So it's within this region. Can you see my mouse head? I hope you can see my mouse head, right?
Yes, sir.
And remember, the V is the austenite region, isn't it? It means in this case, you will have to heat from the alpha plus cementite till you reach the what? Austenite region. But as you reach the austenite region, this V, it must be 55 degrees above it. This part of the V is the A3, while the other one is the ACM. So you must heat within this region of V, heating up to V, at least 55 degrees. So if you are heating at this point, then you add 55 degrees above. Then that's when it will be fully austenized, right? Then you hold it at that temperature and then you cool. This is normalizing. So if you are heating at 0.2% carbon, it means you'll heat up to here. Can you see my mouse head?
Yes, sir.
Then you heat above this 55 what? Degrees above the A3 or ACM. So within this V, whenever you want to, the V depends on the carbon content. So if your alloy is 1.2 here, then you'll have to heat up to the V, then at least 55 degrees above it, somewhere around here. And that's the normalizing temperature. And then you what? You cool. So similarly with full annealing. Full annealing is this dark ash. You can see it looks like an L, though it's a sleeping L. So it starts here. Can you see? It comes here, then it goes parallel. So this is the 8A1. A1 is the eutectoid temperature. Can you see? This is the A1. So it means you must heat within this slanting L. The left side of the L is a bit slanting, while the other side is perfectly horizontal, right? So you must heat at least above this L. So if your alloy is 0.2% carbon, then you have to heat till it reaches here, then above it 55 degrees, and you furnace cooled. If your alloy is 1.0 or 1.2, you heat till it reaches the A1, and then you add 55 degrees above it. This is the A1. So this is it, A3 and A1. In this case, A3 and ACM. For the full annealing, it can be austenite or what? Austenite plus cementite, right? While for the full annealing, you are only hitting to austenize. For the normalizing, it's only within this region. For the austenizing, it's only within this what? Region, right? Sorry, for the normalizing, it's only within this region, the V region. While for the full annealing, is the complete region here, because this region is the L what? Is the L shape, and this is the replica, right? This is the L shape. Well, let me put it this way, isn't it? So for the full annealing, it's hitting above this L shape I just drew, or I just shaded, right? While for the normalizing, it's just these yellow lines I drew within the V shape. So it means within the V shape, we only have austenite, while within the L shape, we can have austenite plus what? Cementite. Just as is given here, you can see this austenite plus cementite and austenite. So that's the full what? Annealing. And if you look at it, this is the A3 and this is the A1 for the full annealing. So let's look at for the spherodizing, and then we call it a day. For spherodizing, it is hitting within this region. So typically it can be three ways. Hitting the alloy just below the eutectoid temperature. This is the eutectoid. So this is the spherodizing here. You can hit above or below. Either you hit above or below or within this range, right? So this is the eutectoid temperature here. You can see my mouse here. This is the eutectoid temperature. So you either, the first one is hitting the alloy at a temperature just below. So you can either hit below it, and this is the time interval for holding, or hitting just above it. So you can hit above it, right? Or hitting alternately within 50 degrees, so above low. So it should be within the A1 line, but within 50 what? Degrees. So this is the last one here, within the A1 50 degrees, or you can either hit above it or hit below it at least 50 degrees, or within the eutectoid temperature. And what is the eutectoid temperature? It's 727. So this is the eutectoid temperature. So either you hit above it or below it at least 50 degrees above it, 50 degrees below it, or within 50 degrees within the line. So briefly, let's look at these three processes: normalizing, full annealing, and then spherodizing. Let's look at them. So let's start with normalizing. Normalizing basically is hitting within the V shape. Is hitting within the V shape and at least 55 degrees above the ACM or the A3. This is the A3 line. This is the ACM, and this is the horizontal line, is the A1. So hitting within this region is normalizing. Okay, let me adjust it a little bit. At least 55 degrees within this region. So this is the 55 degrees, the shaded portion. Sorry. So if the alloy is here, it means one has to hit at least 55 degrees. This is the 55 degrees. And if it is here, so this is going to be the 55 degrees. Next, let's look at full annealing. Next, full annealing. Let me get the spelling correctly. It's double N full annealing. Here is within the slanting L. That's the first part of the V, which is the A3, and this horizontal line is the A1. So full annealing is hitting above 55 degrees. So when you reach the A3 and ACM line, hitting above it at least 55 degrees above it. So the A1 is the horizontal line, and let's so here from 0.7 I'm coming from 0.76 is sitting at the same at the same temperature. So from 0.76 here is 0.76% carbon. So from here at least 55 degrees above A3 and A1. And if your carbon content is here, it means you'll have to hit your 55 degrees is going to be here. And in this case, this is the, so from 0.76 up onwards, as the carbon content increases, the temperature is almost the same. The full annealing temperature is the same. And then lastly, we look at spherodising. Here is within the heating within the A1 line. So it's either you heat above it, as can be seen here, heating below it, or at 700 degrees. So the A1 line is 727. This is the A1 line at 727 degrees. This is the eutectoid line or eutectoid temperature line. So either heating below it at 700 degrees, heating below it at 700 degrees. So let's assume this is our 700 degrees. This 700 degrees mark, or heating above it, that's above the 277 eutectoid line, or alternately heating within 50 degrees temperature interval. So in this case, we assume this is let's assume here is 50 degrees. So heating, it means heating and cooling alternately. So in this case is heating and cooling alternately within the A1 line. So we've come to the end of our lecture today. I think we stop here at annealing processes, and next week we begin from conventional heat treatment. Thank you. Have a nice day. So we meet next week.